Okay, so I started recording.
Okay, thank you. So the topic for today is a proposal that I've been working on for a while about storage capacity tracking. So because not everyone is probably familiar with a problem, let me start with a short problem statement. In Kubernetes, we have two situations where pods are getting scheduled and that scheduling doesn't work as well as it could. That one situation is when a pod has a volume that hasn't been provisioned yet, and the provisioning is waiting for the pod to use, for some pod to use the volume. In that case, there is a scheduler extension built into the Kubernetes scheduler, which triggers volume creation, and there is a mechanism now that also that we fixed for CSI where the pod scaling can move between nodes if a volume can't be created. But even in that case, the Kubernetes scheduler really basically randomly picks a node as far as the storage system is concerned. There's no hint from the storage system to the Kubernetes scheduler that which nodes are actually suitable for the pod. The other problematic situation is with ephemeral inline volumes. There, the situation is even worse. A pod gets assigned to a node permanently, and only then, when kubelet tries to publish the volume, then the operation succeeds or fails. And if it fails because there isn't enough storage available on the node, the pod is basically permanently stuck. So we don't even have a chance with core Kubernetes components to move it to a different node. The only solution in that case is to delete the pod and hope that the next time that it gets created by a higher level app controller, that it lands on a more suitable node. So the proposal that I have pending, it's a CAP called Storage Capacity Constraints for Pod Scheduling, tries to enhance this situation. So it basically it introduces an API that a CSI driver deployment can use to provide information about what's called CSI storage pools in that CAP.
Hey, Patrick, do you want to share your screen to show the CAP?
I can try. The last time I tried it, Zoom failed even more miserably, and I couldn't see anything myself. But let's see whether I'm more lucky. I have a more up-to-date Zoom client now. So, can you see?
Yes, we can see it.
Okay, good.
Very good.
So technology, sometimes it works. So the idea here is to define this as a standard API object type in API server. The reason why it needs to be built into core Kubernetes is that later on we want to use that information also in the normal kube scheduler, and more specifically in the part that is responsible for volume creation and volume scheduling in the kube scheduler. And there is currently no good mechanism to do that with custom resource definitions. And the client bindings also would be problematic. So the easiest path, well, easy in quotation marks, because it is an API change in Kubernetes, is to define these as normal API objects. We've gone through various iterations around that API itself. I don't want to repeat that today unless people actually really want to. The idea in general has been that storage capacity is one use for this API, but not necessarily the only use.
Hey, Patrick, can you hear me? Sorry, this is Hemant here. So, so about the being part of core Kubernetes, scheduler team actually prefers they have a plugin design where external component, externally running plugin can affect scheduling decisions. And I think the scheduler team is quite reserved about like accepting new primitives in scheduler actually, just for reference, and they want everything to be written as plugins.
So the plugin in this case is the plugin that the volume SIG storage already provides for the scheduler. We don't need to change anything between in the core scheduler. All the changes are in that volume scheduling plugin that SIG storage basically has in Kube Scheduler. Now, the other extension mechanism that of course exists is a scheduler extender, which is a completely separate binary. It's basically a webhook. And then it could be done with a CRD, but the entire solution would basically become a vendor-specific solution. I've done that in PMM CSI. I can say from experience that it's horribly difficult to deploy that because you end up with dependencies on how the cluster is configured and whether it's where Kube Scheduler is running, how to reach the pod inside the cluster where your extender runs. And of course, every single scheduler decision then needs to go through the webhook, which has performance impacts.
I would also add, yeah, the scheduler plugin that SIG storage currently provides is compiled and it's in the Kubernetes code base. And to put a dependency on a CRD, I think would be also a non-starter.
Yeah.
But I think so. I believe in this upcoming release, SIG scheduling is pushing us to move our plugin into the plugin framework. So
Yeah,
going forward, everything is going to be using.
The plugin framework is not using dynamic linking or webhooks. It's compiled.
Yeah. It's still compiled in, but I'm just saying, like, in the end, all of this is moving to the scheduler framework. And I think we should also consider, like, I think if I understand correctly, the scheduler extender was kind of the old way at extending the scheduler, and now we have the scheduler plugin framework, which is supposed to improve upon that.
I don't think it does, because you still need to build your own scheduler binary. You can do that with the provided framework, but ultimately you still need to get your custom scheduler running and get the pods that care about that to be scheduled by that additional scheduler.
I think that's fine though, because you can run, like, I believe you can run multiple schedulers in a cluster.
And which scheduler is responsible for a pod which uses a volume that comes from two different CSI vendors?
At that point, you would need some kind of admission mutating hook that sets the scheduler based on the volumes in use, and like you said, it could consume multiple ones. So yes.
But can you have more than one scheduler for the same pod?
I don't believe you can.
Exactly. That's the problem that I see, that we have a storage vendor that just can't take over scheduling for a pod entirely.
I guess, Jonathan, since you have a lot of scheduler background, does the scheduler framework allow, like, just defining optional plugins to include as part of the main scheduler?
You mean like change your cluster config to enable plugins?
Yeah.
It would be relatively easy to do if we don't do it already. There was an intention to improve the scheduler configuration schema that would have made that easy.
But it still implies that the code needs to be built into the scheduler, right?
Yes. I think that for this cat, I don't really see a viable path that doesn't involve changing the plugins in the default scheduler.
Exactly. Yeah, that's also my conclusion.
If the plugins for the scheduler were made to be dynamically removable, what would the impact of that be? In other words, is this an appropriate point to propose a virtualized plugin to the scheduler so that different storage vendors, if they had a need for a scheduler plugin, could provide one that could be dynamically added and removed?
I think that's technically very difficult to do. I'm not aware of any good mechanism to have dynamically loadable plugins for a Go binary. And even if you did, the binary interface would be horrible to maintain in a backwards compatible way.
Yeah.
C and C++ have done that for a long time, and it's really just plain problematic. The standard way of extending something is via remote procedure calls, whether you do that via gRPC or REST interface, but that's the old way of a scheduler extender. That basically has all of these deployment issues. It has the performance overhead.
Yeah, and I would say one of the big goals of the new scheduling framework was to keep it all in process so that caching mechanisms could be used.
Makes sense.
Yeah. So with that in mind, I think the only viable way forward really is to extend Kube Scheduler, and where exactly the code lands, whether it's a plugin, that all can be done according to the feedback from SIG scheduling. Although I think we currently do have the interface defined between the storage specific part, and that's the only part that really would have to be modified. And how that actually gets called by the Kube scheduler is orthogonal to that. So the API review, of course, still needs to happen, but I think my goal for 119, that's really what we are talking about, is to actually decide that, yeah, we want to try to get that API into core Kubernetes. We want to try to enhance the scheduling part. And another goal for 119 is to use that new capability at least for local storage that is made available by some CSI drivers, because that's where it hurts the most when pod scheduling is done wrong or picks the wrong node. And I think I do have some discussion further down the cap. The updating of the capacity information can be done at the moment by external provisioner for volumes that are local, for storage that is local to a node, without changing the CSI spec. We have discussed how to do that with network attack storage, but the problem then is that there's no good interface to discover actually what get capacity call parameters are needed to retrieve available capacity. Because it's unknown what kind of topology the storage system really has. So someone outside of that storage system, like external provisioner, really can't make up the necessary or the correct get capacity parameters to get a useful response from the CSI driver. That part pretty much has to be postponed. It will be necessary to come up with a solution for that, but I would like to postpone that and make it a gate, a blocker for making this whole thing beta. For alpha, I just want to get the API in. I want to have some usage of the API to explore whether it's useful. And yeah, then refine it further, because this could be done entirely outside of Kubernetes, but that because we are talking about a kube scheduler modification and API server modification, I think the right way of doing this is to get it as alpha into Kubernetes itself, where people can collaborate. Otherwise, we create a parallel Kubernetes distribution with this feature added on top, and that just feels wrong to me. that's not aligned, in my opinion, with how Kubernetes itself gets developed. We do have alpha features for a reason, that is to collaborate on them in Kubernetes.
So I wanted to talk a little bit about maximum volume size, if we could.
Yeah, of course.
So I think this is kind of where some concerns have been raised in the past. I think the challenge is calculating volume capacity tends to be different from storage system to storage system. And I want to make sure that what we're doing here would be generically reusable. So as I understand it, we are allowing Kubernetes to be the one that will make the calculation to figure out what a volume size is going to be. And
not quite.
Just wanted to walk through that.
Yeah. So what we have in Kubernetes is just the size, the resource requirement, the minimum size that is specified in a persistent volume claim, and that size is a fixed value. It's a certain amount of bytes, and it's exactly handed over like that to the CSI storage, to the CSI driver. There's not done, and there isn't the plan to do any calculation with that size in Kubernetes. What the cap adds is just this available capacity, respectively, the maximum volume size. And those values are calculated by the CSI driver itself. And the difference is available capacity. Now I need to refresh my own memory again. So the CSI spec has this get capacity call, but it doesn't really specify in detail, in my opinion, what the available capacity means that is returned by the CSI driver. The cap proposes that this gets configured in the external provisioner, that the CSI driver deployment can basically specify in more detail what this value really means. Whether the capacity response is the current total capacity, and that just sums up all the available space. For a storage system that is completely linear and has no fragmentation issues, that's probably the right solution. You can take that available capacity and split it up in whatever way you want. And if you have volume that is smaller than the available capacity, you have a reasonable chance to actually provision it. Now, the other situation is where a storage system actually has fragmentation. And then the total available capacity might be considerably higher than the maximum volume size that actually can be provisioned, because you have one chunk at the beginning, some allocated space in the middle, and some space again at the end. And you can only create volumes that fit into these two parts at the beginning and at the end. In that case, it makes more sense to set the maximum volume size. And the comparison in Kubernetes is the same. If it finds a node or a storage pool where the maximum volume size is smaller than the volume that it tries to create, then it knows that it's basically a negative statement. This pool is not suitable for this volume. And the semantic here is kept flexible. We could eventually we could have a CSI call that says my total available capacity is this, and in addition my maximum volume size is this. We currently don't have that, but the API would cover that because both values can be set.
So in order to make a decision, the scheduler needs to know when it is, I guess before a volume is provisioned, what the size of that volume is going to be, right?
Yes, but that's what we have. We have this, yeah. Well, it does have this, yeah.
Sorry, go ahead.
We do have the size that is requested in PVC. That's the value that Kubernetes scheduler will use.
Right, and so that I think is the concern, because the size that Kubernetes requests may not be the actual size that the underlying storage system ends up using, right? So if I request a 1 gig volume, the storage system may end up consuming 3 gigs to give me that 1 gig volume and eating up more of the actual capacity than expected.
One potential solution might be for the CSI driver, if it has this problem, to reduce the available capacity and the maximum volume size so that these volumes do have enough slack to actually accommodate the up round or the increase of the actual volume size. That would be one way.
Would be nice, but I think the problem is that we can't really predict how a given storage system is going to consume storage. So unless we allow the storage system to make that calculation, I don't see how Kubernetes could do it in a way that would work for all storage systems.
Yeah, I agree. That's why I'm saying that this get capacity call basically artificially needs to reduce the value that it returns by the worst amount that it can potentially consume for a certain volume.
So I guess last time when we tried to propose this, one of the use cases that came up was a storage system where in the storage class you can configure things like the replication factor, and that is going to impact the actual storage that gets taken up. But at the same time, also multiple storage classes can end up sharing the same underlying storage pool. So you can have one storage class with factor 1 replication and another storage class with factor 3 replication.
Yeah, that is covered by the API because a storage pool has a list of information by storage class. So in the case that you have one storage pool and it may end up being used with replication and without replication, depending on the storage class, the available capacity and the maximum volume size will be stored differently and will be populated differently because the CSI driver will get called with the parameters by all known storage classes to make sure that these values really reflect the storage class parameters.
Can you expand on that a little bit? Who's going to do that calculation and how?
So the external provisioner, when this is enabled, will need to watch storage classes for the driver that it is responsible for. And whenever it sees a new storage class being added, it will have to check with the CSI driver what the capacity is for that storage class. And then it needs to update the storage pool accordingly. So it doesn't
basically the external provisioner acts as an adapter to modify the total capacity based on the actual parameters of the storage class?
It basically iterates over all storage classes. And for each storage class, it does a get capacity call. And the CSI driver then looks at the parameters for that storage class, and it's still the CSI driver that interprets certain parameters. It's just that the external provisioner basically does that by storage class.
And if I understand correctly, the point of this is that the kube scheduler will then look up the particular storage class in use for that storage pool.
Exactly, yeah. So the actual comparison takes into account the size and the storage class, and then it walks that CSI storage pool data structure to find a relevant entry that says, yeah, this pool has enough capacity for this storage class, for this volume size, and then it picks the pool.
And so just to make sure I understand, sorry, go ahead, Michelle.
Oh, sorry. No, go.
No, go ahead.
I think the shared storage pools or shared storage pools across storage classes is still a challenge though, because if say you are at very low capacity available, then, and if you had a pod request 2 volumes from 2 different storage classes, but they end up sharing the same underlying storage pool, then you could potentially cause, you could provision 1 volume successfully, but then the second volume might fail to provision because both available capacity values were assuming that it was not, this capacity was not being shared with anyone else.
That's correct. That problem doesn't get solved. Therefore, I think we actually need, eventually, we will need some better solution for handling these multi-volume pods. One idea that I had is that we allow PVC creation in a tentative way. And then if we find that another volume fails, we roll back the binding of that first volume or the other volumes that have been tentatively allocated. Something like that, I think, is feasible, but that's, in my opinion, a separate cap. And even with that, and this cap here is still needed because we still need more information about available capacity to reduce the chance that randomly picking a node will end up on a bad node.
But it's not even like the case of a single pod requesting 2 volumes. You could just have many pods being scheduled at the same time.
Yeah, but then that's where we have, for volumes with delayed binding, we have this pod rescheduling. So basically what happens is the scheduler picks a node tentatively because the current CSI storage pool says that it has enough capacity. But then when the actual volume creation happens, it fails. The external provisioner can use that as a signal that it needs to get capacity, do the CAT capacity again. It can update the CSI storage pool. And the next time that the scheduler gets invoked for the pod, it now has more up-to-date information and can pick some node that actually still really has some available capacity left. We do have this pod rescheduling right now. We fixed it for 118 in external provisioner, but it's currently entirely random whether the next attempt will pick a better node. It might still pick the same node again, and then it will just continuously end up trying to run on the same node that still doesn't have capacity. There have been proposals to model pending or in-flight operations. But it has been pointed out earlier that this is just not possible for every storage system, and therefore this cap doesn't even try that. It still relies on some recovery mechanism for a broken node selection, and that mechanism is incomplete. But we can make it more complete going forward. But I think we should still move ahead with this one here because it does help for some cases already as it is now. And if we make the requirement for anything going in that it solves all problems, we are not getting anything in. That's my concern. We need to start somewhere.
And so I just want to understand the flow a little bit. If I can repeat it back to you, can you confirm? So first step is identifying the capacity of a given storage pool. So the first thing a cluster admin would do is create a bunch of storage classes, then create a storage pool object that points to those storage classes?
No, that's the creation of a CSI storage pools is entirely the responsibility of a CSI driver deployment.
Okay.
So the external provisioner, I picked the external provisioner just as one sidecar where this most logically fits in. It could be an entirely new sidecar. but I felt that because external provisioner is involved in provisioning, it has a chance to notice things like volume created, volume deleted, and when update capacity. So it seemed like a logical place to put it. The flow is external provisioner needs to know that it can do, it needs to figure out what kind of storage pools the CSI driver has. What we can do right now is have a command line argument that says, this driver has node local storage. And in that particular case, the external provisioner has enough information to say, I need to create one storage pool per node with the topology keys that it gets from the CSI driver. And then...
And that would just be temporary, because ideally we want this to work with non-local storage as well, right?
Well, this mode of operation would remain for CSI drivers that just manage local storage. But we can add another mode later on that uses some other way of identifying storage pools.
Mm-hmm.
And then the
Potentially
CSI
like
driver developer, the CSI driver deployment basically, so the CSI vendor, the storage vendor, they decide how to do that, how to identify storage pools.
Okay.
And so the CSI storage pools get created and deleted by the external provisioner based on the information that it gets. Command line parameters, list of nodes where the CSI driver is running. And that's also how it does the get capacity call. So if it knows that it's node local storage, it just does one get capacity call per node with the topology of that node and per storage class. And then it creates that.
How does it do the mapping of the storage classes to the storage pools?
It basically,
sorry, go ahead.
I think it is, yeah. For the simple case, for this load local storage, basically we are telling the external provisioner that the storage class does not influence the node.
That doesn't seem right, because like as an example, you can have on a single node, you can have a pool of storage that's backed by spinning disks and another pool of storage that's backed by SSDs. So those should be two different, so you'll have a storage class for SSDs and a storage class for spinning disks.
Yeah, that case then is not currently handled, or it's not part of this proposal. This will be one of those situations where we need some new API between external provisioner and a CSI driver, which allows the external provisioner to iterate through those storage pools.
So, but in the CSI spec today, the capacity does have the storage class parameters and it has a topology in it. So theoretically, yes, you can iterate through every storage class per topology.
Yeah, but that's what I'm proposing. Yeah, but then you don't know whether that is the same pool. you could have one.
So it sounds like we need a storage pool concept in the CSI spec.
Yes, that's correct. For the general solution, yes. But to get started, for those drivers, and I do have two examples. One is the PMM CSI driver that I'm working on. The other is Topo LVM. They just have one pool per node. And for that special case, we don't need a new CSI API call. And
but I think
that's what
so.
I'm proposing to start with.
When I was working on the local storage feature in Kubernetes, the folks that I was working with, they definitely have the use case of having spinning disks and having SSDs on the same node. It was a big majority of the use cases for local storage.
And I have another kind of example that kind of requires this interaction, I think. But I can bring that up if we want to close on this one first.
I think
so
this is one. This is. Yeah.
Go ahead, Patrick.
I think we definitely need to talk about that interface and how to identify storage pools more. But I also think that it doesn't affect the API. Or if it does, we'll just change the API. It's alpha. And
yeah, I'm less concerned about the alpha. I want to make sure that we have a clean path to GA. So I want to dig in a little bit into what that interface would look like if we made it in CSI. How would we do the mapping between a storage pool and a storage class? So I guess we could have a, get storage pool concept or something. Can you talk about what you think that would look like?
Well, I guess the underlying idea must be that the CSI driver needs to enumerate or list all of the storage pools that it has. And I haven't really thought about the API too much, or not at all, to be honest. I don't know what that API will look like. It may involve returning some of the parameters that select the pool, but I'm basically pulling that out of my head right now. Out of thin air. I really haven't considered that yet.
I think the tricky thing might be. Sorry, I just wanted to say one thing. I think the challenge might be the fact that in CSI, we don't have a first-class concept of storage class. We have an indirect way of referencing storage classes in CSI as opaque parameters. And so if the coupling between storage class and storage pool is tight, even if we make storage pool a first-class concept, it might get tricky doing the mapping. And I just want to make sure we have a clean answer for that. Go ahead.
So just trying to say that in this other cap that Christian proposed earlier, that we do have this controller list storage pool API in CSI. So we can look at that again.
Can you talk about what that would look like?
I looked at that cap and it doesn't. I have looked at that cap and it doesn't really specify a full solution for that either. It has exactly the same issue that the mapping between storage class parameters and the information that was proposed for that CSI interface is incomplete. So I don't think that cap solves the issue either.
So I was wondering, could we enhance get capacity to return an additional argument that said the underlying pool it's based on?
That would be actually a neat idea, that we have one way of listing storage pools, just so that we know that they exist, and then if we call get capacity with parameters that are still opaque, we get the information back what pool that belongs to. That may work, yeah.
Okay, so assuming you have a mechanism in CSI to get a list of storage pools, the external provisioner comes up, it says, give me the list of storage pools you have. It has A, B, and C. Then it iterates over the storage classes that exist in this cluster. And for each storage class that belongs to the driver, it does a get capacity call and gets the mapping from the storage class to the storage pool. And presumably the get capacity call returns a response for capacity that may be lower than what the actual capacity is in order to accommodate if a volume was provisioned with those specified parameters. And so effectively, we've taken care of the issue of striping, mirroring, replication, potentially throwing the calculation of Kubernetes off, because as far as Kubernetes is concerned, a byte is a byte.
Well, no, I think the calculation in Kubernetes is still off because of the shared pool model.
Can you explain that?
So like for a single volume, the calculation is fine. But once you consider multiple, if you're considering multiple volumes in the same loop, then
Right,
the
right.
capacity information is
Yeah.
not correct, because it's basically assuming full capacity per volume, and we are not really able to take account for the fact that we have sort of reserved this capacity for some pending provisioning operation.
Yeah, that's correct. But I don't see a solution for that in Kubernetes, because modeling the effect of pending operations, that just gets way too complex and or incomplete, that it just won't work in practice.
So scheduler kind of has to deal with the same limitation that, you know, 2 pods could be scheduled in a way that consumes more resources than are available. And this is just done with allowing whoever loses the race to fail and then retrying.
Yeah, and that's the goal here, that we increase the chance of not making bad decisions, but we then have a plan B if that decision turns out to be, yeah, if a pod loses a race, that we then recover from that. And that recovery still needs further work, but we can work on that in parallel, or
Yeah,
after one
because
after the other.
I think the main difference.
Both needs to be done.
Yeah. So just to clarify, I think one difference between storage allocations and something like CPU or memory is that in the storage case, we are actually binding in 2 objects together one to one, and it's basically, it's very hard to undo that binding once we do it.
I haven't said that it's easy.
What do you mean by that?
But
So like in the case of, say, CPU, if you overcommit the CPU, that's okay, because you could just reschedule the pod to another node.
Yep.
But in the case of storage, if you bind one volume, but then if you bind the second, if you try provisioning the second one and that fails, now you've already been bound. The first one's already bound, and that first one is sort of fixing you to this node, and you can't really roll back.
So if your first decision was inefficient, you're basically screwed for the subsequent decisions. And the only way to fix that would be to hand the scheduling decision off to the storage system completely instead of letting Kubernetes try to do it.
No, I would argue that we need I think one solution that was proposed is a reservation system, but that's a completely new concept, and it basically amounts to just trying the volume creation, keeping the volume alive as long as the scheduling is still going on. I think the most viable approach is to have a rollback for the volume provisioning for volumes that have not been used yet. So we know that we can destroy them because they've never been used by a pod, they don't contain data. Therefore, we can destroy them. If we keep track of that, then we may be able to add a rollback mechanism that says, okay, we've allocated some volumes for this pod. We couldn't allocate all of them. Just return the space that we have already allocated and try again with more up CSI storage, pool information, ideally elsewhere.
A crazy idea. I wonder if the data populator work could potentially help here, because I think the current idea being explored with data populators is a way to sort of provision intermediate volumes, don't make them available to the workload yet.
Right.
And then when the data is done populating, then we switch it over to the user's PVC.
But you still need, with the data populator stuff, you still need a way to get an empty volume in the right place with the right performance characteristics and the right locality, all the other things you care about before you put the data on it are still problematic.
Yeah, I'd like to move back to this cap here, because what we are now discussing is really a separate enhancement proposal that needs a lot more thought. I fully agree that we need it, and I wouldn't even move this cap here with storage capacity forward from alpha to beta unless we also have an answer to that other problem, like concurrent ports with multiple volumes. But I would like
That's
to
fair.
not spend more time on it here, because that really hasn't been defined. There's no proposal. We are still basically brainstorming now.
Yes,
And
but however, I want to avoid keeping features in alpha for a very long time, because there is a push from SIG architecture that there's a push from SIG architecture to promote features from alpha to beta to GA in a short amount of time, which sort of implies that even when we go to alpha, we should have a clear idea of how we're going to get to beta and then to GA.
Yeah, I hate to bring up more gaps, but let me point out that the other issue that I currently still see with this cap here is inline volumes. Because the way how they are currently handled, the initial idea that I had was that if we just add a size parameter to the inline volume spec, then we can use the information that comes from this cap here with storage pools if we allow for the special case that the inline volume doesn't have a storage class, for example. So that would be, in my opinion, the low road to fix this problem for CSI thermal inline volumes. Add the API, this API extension with a size, use that size, and we are basically done, mostly done for capacity tracking. The problem remains that the recovery is incomplete for inline volumes, because it's still we still have this problem that we make some more educated choice, but it might still be the wrong choice, and there's no recovery mechanism, no suitable one for inline volumes, for pods with inline volumes, because they are provisioned or they are starting up on a node, and the only way to recover is to delete them, which can be done with this one external component. I forgot the name. I think it's somewhere in the cap, but the point is that the descheduler, right? But that's not a standard component. It also doesn't currently support the recovery from this particular case. So the descheduler would need to be extended to handle a failed volume creation, because currently it doesn't deschedule such pods. That's why on the SIG storage mailing list, I brought up the idea of implementing CSI ephemeral volumes differently, such that they get mapped to persistent volumes and then get provisioned like normal persistent volumes through the mechanisms that we have with external provisioner, perhaps even. And the only difference would be that they get defined inline and that their life cycle is tied to the pod. That solves the recovery situation for inline volumes. But it's another big change, and there has been some concerns. My first idea was, okay, let's create a new source for a volume, let's make it a persistent volume template, and then some controller can create an actual PVC in the same namespace as the pod on behalf of a pod. And that PVC then triggers provisioning. We have a bound volume, perhaps tentatively, same mechanism as for normal PVC. The difference is that via the owner mechanism, that PVC gets deleted together with the pod, and therefore has a life cycle that is tied to the pod. Now, Saad has this concern about creating a user visible object, the PVC, automatically through the controller. But I think that's not that unusual. Other app controllers do the same thing. They create additional objects, and those objects are visible, and people might do something with them. But I think that this idea still has merit, and I want to bring it up because that, to me, is even more important than figuring out how to handle pods with multiple volumes or pods or with this heavy load situation, because even on a lightly loaded system, inline volumes, when they land on the wrong node, that's just bad, and I want that problem solved too, even before the others.
Sorry, time check.
So we don't.
2 minutes left.
Yeah. So
I think we made good progress today because there were a handful of concerns that I am no longer concerned about, but I think there's still a couple of open issues. So maybe let's schedule one more meeting to talk through those.
Yeah. Okay. My question is, how do we prepare for that next meeting? What do you want me to do to address other concerns?
I think the two main concerns right now are the multiple volumes scheduled in a very short amount of time. And if we have a viable solution for that, I think that'll unblock the alpha. To Michelle's point, it looks like SIG architecture is encouraging us to have a plan not just for alpha, but kind of a path towards beta before we start implementing the alpha. And if that's the case, these kind of hairy edge cases, let's kind of think through them and see if we can come up with a potential solution. It doesn't have to be implemented for alpha, but if we know, oh yeah, for beta, we want to consider something like this, I think that would be good.
Okay. So that means basically writing another cap for volume recovery of volumes. I can try to come up with something. I have this one idea in my head that I just need to think through.
Right, and if you want to brainstorm on a meeting, that would be perfectly okay too. Like I hate to kind of put more work on you, so if you want to like get everybody in a room and say let's bounce ideas off each other and see if we can come up with something together, that would be okay too. Whatever you're comfortable with.
Yeah, I think I need to think through some of this myself first, and then I may have a more specific proposal, whether it's a cap or just some Google Doc with some rough ideas. That may be one thing.
Okay.
But I also need to know how we move forward with ephemeral inline volumes.
Yes.
Because I don't want to lose track of that particular problem.
I think we should separate it, because otherwise this cap is going to be way too big.
So, definitely. So my current proposal here in this cap, I've updated it last week or this week, I don't remember. There's one section about how to handle ephemeral inline volumes, and it basically has two solutions in this cap here. One is the size extension, and the other is this completely new idea of mapping it to PVC somehow. And I don't intend to put that into this cap. This cap just says this information that we have here can be used also for ephemeral volumes, but how to do that needs to be separate. The question is now, which path do we want to pursue? Do we want to keep extending the current CSI ephemeral inline volumes, or do we want to try something else? And if so, would it be viable or would it be acceptable to have a controller that creates PVCs? Because I think that part. Yeah.
I'm sorry. I think we should keep that to a separate discussion, right? Because it's kind of orthogonal to this.
I mean, the same argument can be made as the multiple volume scheduling, right? That I feel like this would be a blocker for getting it to beta now.
Yeah, and it's also, in my opinion, it's also blocking ephemeral inline volumes from going from beta to GA.
Yeah.
Because we know that ephemeral inline volumes have problems for some people who are trying to use them, including myself. Right. And that's why I want to get this problem solved.
They're both very closely related. So I fear if we kind of say, oh, it's a separate problem, we're going to come up with something here that doesn't mesh well with ephemeral inline. And we're going to be kind of stuck on both sides in the future.
I think we need to discuss this a little further, and I regret I have to drop at this point, but I look forward to follow up on this.
Can we schedule another meeting with follow-up discussions? We can't get it solved
please.
now. It's already past the.
Please do. And my question is, I can prepare also some ideas for this mechanism for mapping to PVC, but I want this one question that really is burning on my mind is, would it be acceptable to map it to an actual PVC object? Or is that a non-starter?
It seems odd to me, honestly. I think if we were to do that, the reason we would be doing it is because there's a missing object that basically allows you to represent volume capacity. And in lieu of that, we're using PVC as kind of a hack. And so it may be worthwhile to consider what a new object might look like.
No, I think PVC is perfectly fine. It does have all of the information that we need. It has a storage class, it has a size requirement. It is basically the request to provision a volume.
Right.
So I don't think we need anything else. The only thing is
ideally. Sorry, go ahead.
Yeah. The other alternative that I had.
Sorry, go ahead. There's a delay.
I had a plan B, and that is keeping the PVC inside the pod and just change the external provisioner and all components that currently work with the PVC for provisioning purposes such that they also look for the same information inline in a pod. So we never split out the PVC from the pod. We just change where we make changes to the PVC. So any read or write that currently goes to a PVC would go to a PVC embedded in a pod. But I like that less than actually splitting out the PVC. The main disadvantage is we would need to modify all other components to work with that model. It can be done, I think, with a translation layer, something that sits between reading PVCs and modifying them, and then just redirects these reads and writes to where the PVC actually lives, whether it's a separate object or embedded. And then the rest of the code in external provisioner, for example, would be mostly the same. But then we get weird situations like where in the pod spec, we have an embedded PVC and a status update inside that spec. It feels weirder than splitting out an actual PVC.
Yeah, it smells weird to me because it's it's not a user created object. The whole life cycle of it is going to be created by Kubernetes, deleted by Kubernetes, and tied to the pod object. And so when you have an object that's the life cycle is tied to the pod, there's the potential for skew where the object exists after the pod is gone and things like that. It gets weird.
Oh, like
but then
solved.
Yeah, even with the ownership, that's fine. Either we block. I actually would block the deletion of a pod object while there are still PVCs tied to it. And even if the API server decides to go ahead and delete the pod, we would still have this pending PVC as the place where we store information, where we know that this will then become deleted. It will basically still live as long as the volume exists, but it will get garbage collected. So I'm not concerned about that. It's the same model that other app controllers have, where a deployment instance object, for example, creates a replica set, a replica set creates a pod, a stateful set also creates PVCs. All of that is perfectly normal.
Sorry,
Okay.
we are over time,
Over
so
time.
we
Yeah,
definitely
thanks.
need another meeting.
Yep.
Yep.
All right. Thanks, everyone.
Thanks. Yep.
Take care.
Goodbye.